Hello, so welcome to the final part of this chapter, and in this part we're going to be looking at power. Okay, so previously we've looked at work. So again, work is force times distance, and what that essentially means is when, let's say, we're pushing an object, so let's say we're pushing a box forward. Work basically tells us how much energy we're transferring, how much energy we're putting onto the object to move it forward. Okay, but actually, what we kind of worked with, no pun intended, is that it was a fixed number, right? When we worked out the work done, it was always just a number. So it's just a fixed constant number. But in reality, work will change, right? Like, it will change over time. So if you really think about it, let's again think back to pushing a box or even working out or doing something physical, right? Are you going to be doing the exact you're going to be putting in the exact same work all throughout the time you're active? No, there's going to be a bit of times when you'll be achy, and there might be times where you have a bit more power and a bit more force. So it changes, it fluctuates, right? So the actual force we put onto an object, the work done to move it, is going to change. Anyway, so then that leads on to the idea of power, and actually power is, I write it here, power is the rate of work. Okay, so that tells us, in other words, more simply, so power tells us, I'll do it here, the work done, obviously to move an object, right? The work done uh, per second. Okay, so it's this idea of how much work we're doing, but the rate, so how much we're doing per second. Okay, so a high power means we're doing a lot of work. A lot of work every second. Low power, less work. Okay, that's the idea. Okay, so then as a formula, then it turns out that power is the specifically the driving force. So remember, that's the force that acts forward to move an object forward. So driving force times the speed of the object. Okay. And so obviously we've got the unit. Well, the driving force is in newtons, as is the force. Speed is in meters per second. So you could have the units as newtons per meters per second, but actually what you'd be more familiar with is that power can actually be watts. Okay, quite interestingly. Again, if you do some clever work, if you look at other formulas, combine stuff, eventually you can deduce this, but I won't. I'll leave it there for now. I'm not a physician, so it turns out power is in watts. Okay, and so I'll highlight it here. Okay, or more succinctly, we can just say that power P is dV. Okay, but obviously P is power, D is my driving force, and V is speed. Okay. And all we'll be doing is we'll just be implementing this formula in this section. So we're going to just look at a bunch of questions now. Okay. So here are okay. So I got this question first. I'm told a car is traveling at 15 meters per second, and its engine is producing a driving force of 1,000 newtons. Calculate the power developed. So it's asking for the power effectively. So we know that the power, again, power is the driving force times speed, which again, as I recall, we literally just went over it a second ago here. So just simply using the formula, just simple use of a formula. So the power of my driving force, I'm told, is 1,000, and my speed is 15. Very simply, multiply them to get the power of 15,000 watts. Okay. And so there we are. Okay, so now we've got this question, and I'm told the engine of a van is working at 5 kilowatts, and the van is traveling at 18 meters per second by the magnitude of the driving force. So essentially, he wants the driving force. Okay, so again, he's talking. It's not explicitly mentioned power here. However, um, it says the engine of the van is working at 5 kilowatts. That's actually kind of very subtly hinting at the rate of the work done. Okay, so the engine is obviously pushing the van forward, right? The driving force. So the engine's pushing the van forward. The engine is working, so it's the rate. So that means the power is 5 kilowatts. Okay. Pay very special attention. Some that they like doing that sometimes. They don't explicitly mention power. Um, working very specifically means power. Okay, because remember, power is the rate of work. Okay, so the power is 5 kilowatts, but it has to be in watts. That's going to cause an issue. It's in kilowatts. So remember again, a kilo is 1,000, so we need to multiply by 1,000, which is going to be 5,000 watts. Okay, and so at that point again, power, I'm going to say P is D times V, so power is driving force times speed. So that means 5,000 is going to be D times the speed. Now the speed is 18. Okay. Therefore, just divide by 18 to get the driving force to be 277.78 newtons. And there we are. Okay. Okay, so now I've got this question here. A car's engine is working at 15 kilowatts. The car is traveling along a horizontal road. The total resistance to motion has magnitude 600 newtons. Calculate the maximum speed. Okay, so this is going to now involve a bit more than just using a formula, unfortunately. So again, to help, let's just draw the situation. So we've got a car on a road. So if I just draw a road like this, simple diagram. This is my car, this little box here. Okay, should be very familiar with these sort of diagrams by now. So we've got this car. Again, the car's engine is working at 15 kilowatts. So my power is 15 kilowatts. But of course, as I just said, it has to be watts. So to get rid of the kilo, times by 1,000 to get it in 15,000 watts. And there we are. So, okay. I'm also told the total resistance to motion. So resistance again is going to be a backwards force, and that'll be 600 newtons here. Okay. Okay, but it's asking me to calculate the maximum speed. Okay. But actually, before we do go on to that, there will also be a driving force, wouldn't there, pulling it that makes the car move forward. We know there's a driving force here because power's mentioned. Remember, the formula is power is driving force times speed. There has to be a driving force for there to be power. So if we have power, we need to add on a driving force forward. Okay, so there we are. Okay, so maximum speed. Right now we get so maximum speed. Uh, okay. That means, and you do need to know this. Even if you remember from normal maths. But if you don't, here we are. Maximum speed means acceleration is 0. So 0 acceleration. Okay. So if you see a mention to either maximum speed or constant speed, there's 0 acceleration. I'm going to mark that on my diagram. So that means I'm going to draw 2 arrows. So 0 meters per second squared. So the acceleration is 0 there. Okay. But it's also going to travel with speed v. Okay, that is my maximum speed. Okay, hopefully you understand my diagram here. Single arrow line to represent speed, and my double arrow to represent acceleration. We will be using speed and acceleration. So hopefully my diagram's clear. Okay, hopefully you're with me up to here, right? Okay, so then what's my maximum speed? Okay, well, we have power, right? So I know that again, power P is my driving force D times speed V. I know my power is 15,000 is dV, okay? But I want to find V, the speed, right? Well, then I need to find D. So what can I do here? Well, this is where I'm going to need to resolve, right? So this is F equals ma. So if I resolve forwards and backwards, right and left, okay? So firstly, the right force is going to be D, take away the opposite force of 600, and that's going to equal ma. Well, the mass, we're not given a mass, but it doesn't matter because remember, mass times deceleration is 0, so it just goes to 0 anyway. Therefore, we just get the equation D is equal to 600. So there we are. So now we can finally use to find V. We can finally find V. So 600 times V is 1500. Again, I'm just subbing D into this formula here from the power. Therefore, V, if I divide by 600, 25. And there we are. That's the maximum speed. Okay. So yes, we will be resolving um, in a lot in this video. And so again, if you haven't seen it in normal maths, make sure that makes sense. But there we are. Okay, we've got this example here. So now I'm told a van of mass 1,250 kilograms is travelling along a road. The van's engine is working at 24 kilowatts. The constant resistance to motion is 600. Calculate the acceleration of the van and the maximum speed. So it's kind of similar, but it's still a bit different to the last example. But let's have a look. Let's try and figure out what's going on. So again, immediately I can spot this. The power is 24 kilowatt, and again we need to convert that to watts. So that's 24,000 watts times by 1,000, right? There we are. Okay, now if I draw the situation again, it's on a road. I've got my van. I'm also told the mass now, which is 1,250 kilograms. I've got resistance, my resistance force, which again, if the van is going to be moving forwards, the resistance will act backwards like this, and that'll be 600. And then there will be a driving force because there's power involved. Power means there's a driving force moving it forward. I'll call that D. Okay, and there's also going to be some speed and acceleration. So firstly, speed. I'm told the speed is 6. Okay. Now the acceleration is what they want me to work out. It's asking me to work out the acceleration at this speed. I'll call that A. Okay. So I need to figure out the acceleration. Okay, but quite a bit of stuff going on here. Okay. Right, so hopefully with me here, I think this is the hard part, right? Once you've got your diagram, you've got all the information, it's just formulas at this point. Hopefully you're with me up to here. Right, so again, I'm going to look at my power equation, so I know what power is. So power P is driving force times speed, but I know my speed is 6, right? Okay, but I also know my power is 24,000, so I can add that on. So 24,000 equals 6 times D. And actually then I can find my driving force, right? If divide by 6, I get 4,000. So there we are. Okay. I can add that onto my diagram then, to make it easier to visualize what we have. So they want me to find the acceleration. So I'm gonna have to resolve, right? I'm gonna need to use F equals ma. So if I resolve again, forwards and backwards, left, right, and left. Well, my right force is my driving force, which we found to be 4,000. Take away my backwards force of 600, my left force. And so that will equal mass times acceleration. Again, F equals ma. So the mass is 1,250 times A. So lots of A. Well, actually, then, if I just simplify this equation, that would be 3,400 equals 1250A. Then I can just divide by 1250 to get A. And I get 2.72. And there we are, meters per second squared. Okay, and so now in part B, it's asking us to find the maximum speed of the van. Okay, so if I sort of draw this sort of new uh, thing, this new case that's going on, this new situation here. So I've got my van. Again, it will have the same mass, 1250 kilograms. The resistance force is still going to be 600 because it's constant, which means it will always remain the same. So it'll be 600 again. So that'll go back 600. Um, the power of the van is still 24 kilowatts. The power remains the same as well. So 24 kilowatts. Well, that's 24,000 watts. So that's my power. Okay. And so again, there will be a driving force again acting forwards because power exists. However, in this case, power, not the power, the driving force, is going to be different. So I'm going to say D dash, okay, to signify it's a different D. Okay, so it's a different force to in part A, because the driving force now may change because the speed is going to change. Okay, so the speed changes, it's likely the driving force will also change with it. Okay, because in part B the speed is different. It wants to find the maximum speed now. And so the maximum speed, again, that's when the acceleration is 0. Okay, so I'll say the acceleration is now 0 because it's at maximum speed. That's what it means. Again, the speed is v. This v. I want to find v. Okay, so that's the situation here. Okay, so again, we've got power. Again, we know that power is driving force times speed. So it's going to be d dash, which is my driving force here, times my speed v. Okay. Well, my power is of course 24,000, so that's going to equal d dash v. Okay. Right. Um, so if I want to find v, I'm going to need to find my driving force. Okay. How can I do that? Well, if I now resolve, because I know my acceleration, forwards and backwards. Well, my forwards force is my driving force d dash. Take away the 600 newtons acting to the left. That's going to equal mass times acceleration. So 1250 times the acceleration. Well, the acceleration is 0. So actually, this again equals 0. So that just means my driving force is now 600. And you can see it is different because my driving force in part A was 4,000 newtons, but now it's gone down to 600. So it may change, okay? So there we are. But now I know my driving force, so then I can use this, my power, to say that, well, 600 times V is going to equal 24,000, which therefore means my speed V is going to be 40, okay? So that is my maximum speed, okay? Cool. Okay, so hopefully you got the sort of gist now of how we use power. Now we're going to look at more problems with angles. Okay. So we've got this example here. So now I'm told a car of mass 2,600 kilograms is traveling in a line. The instant when the speed is v, the total resistance is a variable force of 800 plus 5v squared newtons. The car has a cruise control feature, adjust the power to maintain a constant speed of 18 meters per second. Find the power when, firstly, the car is on the horizontal road. So a horizontal road means it's completely flat like this, okay, like we used to, right? Okay, so if I add my car, here we are, the mass is 2,600 kilograms. Okay, now, I'm told the speed is v. Okay, however, um, they've told me actually speed is constant at 18. Um, so actually I can just change that to 18, really. So there we are. Then we have a resistance again, a resistance force, which is 800 plus 5b squared. Well, again, b is equal to 18 because they just told us it's 18. I don't know why they've introduced a v then when they just told us the speed, but there we are. So v is 18, so therefore my resistance, well, my resistance force is 800 plus 5v squared. Okay, so if I just literally sub v in, I can get a number for this. 800 plus 18, 5 lots of 18 squared. So therefore work that out. That's 2,420 newtons. Okay, so I can add that on to my resistance here. Okay, there we are. So hopefully with me here, so the speed is 18, I'm told it, and then I can work out my resistance as well. There will also be a driving force because there's power. I'll call that D. And so speaking of power, they want me to find the power. So my power is again speed, which is 18 times driving force D. So then in order to find my driving force, I'm going to resolve forwards and backwards as usual. So I got my driving force forwards, take away my 2,420 backwards. That's going to equal mass times acceleration to 2,600. Now the acceleration, they've not told us explicitly, but I'm told that the speed is constant, which again means the acceleration then has to be 0. Okay? So constant speed, so the acceleration is 0. So actually, it's equals 0. Okay? So therefore, my driving force is just 2,420. Okay? Now we can easily work out power. Sub D in 18 times 2,420. Get 43,560 watts. And so there we are. Okay, now in part B, now we're going to look at angle and angled slope. So now we're told the car is travelling up a road that's inclined at 4 degrees. So it's going to look like this. The angle probably is going to be a bit off, but I'm not that worried about that. So there we are. So again, we've got our car on this sort of surface that's 4 degrees, right? Again, the mass is 2,600. Again, sort of the numbers are going to be the same. So the speed is still 18. So it's going to go up the slope with speed 18. The resistance is going to be, well, still 2,420. And then obviously again, there's going to then be a driving force forward, which may change because the forces have changed. So I'll call that D dash, right, for a new driving force. Okay. So I need to find the power in this situation here. Okay. Right. I think that's everything. Oh, and also the acceleration is still 0 because it's constant speed. So the acceleration is still 0 because it's still constant speed. So that's everything. Right. So again, I want my power. I want my power, which is going to again be the speed of 18 times my driving dash. Okay, so I need for my driving force effectively. Okay, so again, to do that, I'm going to resolve oh, um, across what we call parallel to the surface. So up and down in this sort of fashion, okay, up and down the slope. So the forces that align up and down the slope, well, firstly, forward up slope is this D dash. Take away, obviously, the back down the slope 2,420. However, there will also be weight. So remember, the weight acts straight down. That's 2,600 G. But of course, we should then split up the weight into this sort of way. So again, the angle here is going to be 4. So if we again, if you as we said before, if you use SOHCAHTOA with this triangle, so again, this length is 2,600 G. If you use SOHCAHTOA, you get 2,600 G cos 4 degrees and 2,600 G sine 4. Okay, for these two sides here. Now, the force that acts along the surface, you can tell it's going to be this force here. It's 2,600 G sine 4, and that's going to equal 0 because deceleration is 0. Okay, so that's just resolving forces on an angled plane. We've seen some examples previously, and hopefully you're familiar with this. So there we are. So if I just rewrite this, bring it over here to make it clearer. So we have a driving force, take away the resistance, take away the weight that's along the surface. So now we just simply solve this equation for D. So D dash is going to equal, well, 2,420 add 2,600 G, which is 9.8, times sine 4. We get 4,197.4 newtons there. So that's my driving force. Therefore, my power over here is going to be 18 times 4197 times 4, and that will get me 75,553.11 watts. And there's my power there. Okay, cool. So it's the same idea, but now we just obviously it's on the surface, so our resolving is going to be a tad bit different. Okay, but there we are. Okay, so we've got this question here. So here I'm told a car of mass 1,100 kilograms is traveling at a constant speed of 15 along a straight road, which is inclined at 7 degrees horizontal. The engine is working at a rate of 24. So again, working rate, that's the language for power. Okay. So again, that means the power is going to be 24 kilowatts. And again, the kilo it just has to go to watts. So we need times by 1,000. You get 24,000 watts. Okay. Okay, so now if we actually draw the situation, so again, I've got this angled slope. It's 7 degrees. Again, I've got my car is going up this little road at the angle 7. So I've got my car mass is at 1,100 kilograms. The speed is 15. Up the road, and because it's a constant speed, again, the acceleration is going to be 0. There we are. Again, we got we got our forces. So firstly, again, we've got resistance. So the resistance force acting that way. I'll call that F for, I don't know, like friction or something like that. So that's my resistance, and then my driving force is moving my car forward. Again, driving force because there's power involved. Okay. If I will add my mass on. My weight, sorry. So that's mass times G, so 1100 G. Okay, hopefully we'll be here with this diagram. That's pretty much it. Let's see what we need to work out. We need to calculate the resistance force, essentially. So we need to find F. Okay. Okay. Well, firstly, I already have my power, so let's use that. So again, power is force times no, driving force times speed. So P equals dV. But I know my power is 24,000. I also know my speed is 15. There's 15 lots of my driving force D. So therefore D divided by 15, I get 1,600 newtons. Okay, so I'll add that on then. Okay, cool. Right, but that's not my friction force, unfortunately. My resistance force. What can we do now? Well, we can then resolve. Okay, I know my acceleration is 0. So if I resolve up and down the surface along, then firstly up the surface is 60 is my 1600. Take away my resistance F. Take away, and then obviously there will also be a weight as usual. I need to split the weight up in the way. So 1100 G cos 7 and 1100 G sine 7 here. Okay, so this 1100 G sine 7 here, that's going to again be matching the slope, so that's going to act downwards. So that's going to be taken away. And so that's going to equal 0 because the acceleration is again 0 because the speed is constant. Okay? I can actually work out F then. So F is going to be 1600 take away 1100 G sine 7. So if I just put all that in the calculator, I get 286.25 newtons. And there we are. Okay, that's my F there. And there we are. That's my resistance force. Cool. Now I'm told the rate of working is now increased to 28 kilowatts. So the power's changed. Okay, and the resistance is not changed. Okay, so the power's changed, but not the resistance force. Okay, so I'll make a note of that. The power is now 828 kilowatts. And again, in watts, that's 28,000 watts. Must do that conversion to watts. Okay, so then if I draw the situation now, draw this diagram. Again, it's still at 7 degrees. Again, not accurate, but there we are. Again, still got my car, that's 1100 kilograms. I have my resistance force, F, which I'm told is the same. So it's still 286.5. I'm going to have a driving force which probably will change now, so I'll call that D dash for a new driving force. Okay. Now, the speed will change as well. However, we're assuming that the speed will still start at 15. Okay, so the speed will now change. It won't be constant. But because we're only asking for the initial acceleration, so at the start it will still be 15, but then the 15 will change. So the speed is still 15 initially in this situation here. Hopefully that made sense, okay? So it's still 15 here. Okay, so there we are. Again, the acceleration is what we want to work out, the initial acceleration after we change the power. So there we are. Okay, so hopefully you are comfortable with this new setup we've got here. Okay, so we want to find the acceleration. We know our power. We also know our speed. So actually we can work out a driving force. So power is again D dash times V. My power is 28,000, sorry. That's going to equal D dash times 15. So therefore my new driving force is going to be 1,866.67 newtons. There we are. I could add that on. Okay, cool. Okay. So if we want to find the acceleration, so we're going to use F equals ma. We're going to resolve again in the same way. Our forces. Okay. Actually, I do it down here, not to make it too messy. So if I resolve again here. So firstly, the forces up the surface. Again, we've got my driving force. So 1866. 0.67, and then I have my resistance the other way, so take away 286.25, but of course there will also be weight involved. So again, my weight 1100 G, and then split up into these two parts. So again 7, so that would be 111 G cos 7, 111 G sine 7. So again, we want to use this one, the 1100G sine 7, because that's again matching the direction of the slope, but it's going backwards, right? It's going to the left. Okay, so take away 1100G sine 7. So then that will equal ma. Now the mass, sorry, the acceleration is no longer 0. Okay, it's changed. So mass is 1100, so 1100 times a, the acceleration. Okay, the mass times acceleration there. Okay, so I can work out a now. Okay, so if I now just simplify this equation, I get 266.668 blah 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 equals 1100a. Therefore, just divide to get a to be 0.24, and so there we are. That's my acceleration. Okay, so now we're going to look at final set of questions. So we're going to look at some exam questions in a bit. We're going to be looking at now power involved with towing problems. So you would have seen this from normal maths. Problems where you have like a car that's towing a caravan or some piece of weight or something like that. You can see it in this example here. Okay, a car towing some little, I don't know, little thing there. Okay, so this is from normal math. This is from year 12. But depending on how you do this course for further maths, sometimes you might do it before normal maths. So and anyway, it's just nice to have a recap of the essential skills you need. So what I'm going to do with this again, this sort of problem, this was taken from an A-level maths past paper. I'm going to go over it quickly, just this little question here, just to demonstrate what you need to know, because you're going to need to know how to solve a problem like this in order for the other problems in a minute, okay? So very quickly, so this is the situation we've got going on. As I said, I've got a car that's towing, again, being towed by some little rope here in the middle, towing, acts like a caravan or something like that. And so, if I if I draw this out a bit bigger, okay, so we're on a road. I have my car. Now the car, the mass is 1200. Okay, it's been towed by I'm gonna say a trailer. A trailer. Okay. Um. This thing here. All right. This thing here, and that has mass 400. Okay. Okay. So I'm just drawing it out. In this way. Now. Now. Before we look at any other forces, uh, I need to talk about this little rope that's towing the two things together, that's connecting the two things together. So the car is towing the trailer by this rope here. Now, if you kind of split it down the middle, what you need to know is that there's going to be tension towards the car. The tension is going to move away from the car because the car is going to have a driving force. Okay, I call that driving force D. So hopefully that made sense. So the car will have a driving force that moves the car forward, but then the tension, which is basically the force in the rope towards the car, is going to move away from it. On the flip side, then the part of the rope that's towards the trailer will then have tension going in that way to pull the trailer forward. Okay, and so there we are. Okay, so you need to know that the tension is in the rope and it splits in this way. Okay, towards the trailer, towards the car. Okay. Now, there's also some resistance forces, so again, like friction on the road. The friction again is going. The resistance will be separate. Will be different on these two, on the car and the trailer. Firstly, then, the resistance on the car is what we call 2R. Okay. 2R. So how we can add that on here. Okay. So that's 2R. That's my resistance. Okay. Again, that's going to act. If the car wants to move forward, uh, uh, then the resistance is going to act backwards. Okay. The resistance of the trailer is just R. So R there. Okay. Hopefully, hopefully that made sense. Those are all the forces. Okay. No more forces. Okay. So that's the setup. There's also going to be some acceleration involved. Now, the key thing here is because, again, they're connected, they're going to share the same acceleration. So the car move forward, acceleration is A. That's going to match the acceleration of the trailer. Okay, that's the key thing is that their accelerations are the same, and also their speeds. Okay, but we're only dealing with acceleration here. Okay, that's the setup. Okay, that is the setup. So very quickly then, I'm also told the driving force of the car is 7,400. So actually, I can say that the driving force here is 7,400, and also the tension in the rope is 2,400. So again, my tension, which is T, 2,400 and 2,400 there. Okay. So we need to find the acceleration. So the approach here is what we can do is look at the car and the trailer separately. Okay. Again, all of this you hopefully should be familiar with if you've seen it in normal maths. But here we are. So we're going to look at the car first. So if I literally then to make it easy to visualize, I'll just draw the car on its own. Okay. Again, it's got driving force forwards of 7,400. We got my resistance force of 2R and my tension force of 2,400 and the acceleration A. That's literally it, okay? So I'm going to use F equals MA. Again, I'm going to resolve forwards and backwards. My forwards force is of course the 7,400. Take away the obviously these two forces backwards, so that take away 2R, take away 2,400 equals MA. The mass of the car is 1,200 times the acceleration. Okay. So if we simplify this equation, we get 1200A plus 2R equals 5,000. So 7,400 take away 2,400. Hopefully you understand how I got to that. I just literally simplified the equation. Okay. Right, that's the car. We're going to do the same thing with the trailer. And again, I'm going to just focus on the trailer. So if I just draw the trailer bit out, again, I got my trailer. The mass of the trailer is 400 kg. And so as you can see here, the force forward is 2,400. And the force backwards is R. Okay, my resistance. Again, the acceleration will also be A. Same one. Okay, so if I then resolve forwards and backwards for the trailer here, we get 2,400 take away R, going to equal MA. The mass is 400, lots of A. So again, we get this equation for 100A add R equals 2400. Now, what you notice then is what these two different equations, one from the car and one from the trailer. And hopefully you notice we get some simultaneous equations. Okay. So 400A add R is 2400 and 1200A add 2R is 5,000. So at that point we get these two equations simultaneous. We just we just solve them like any simultaneous equations. So we need to find A. So very quickly, what we can do is times the first one by 2, let's say, to get 800A. Add 2R equals 4800, and then we can take these two away. So 1200A take away 800A, 400A. 2R take away 2R goes to 0. 5,000 take away 400, 800 is 200. So then to get the acceleration A, well then we just do 200 over 400, and so doing that will get me the acceleration of 0.5 meters per second squared. There. Okay, so there we are. So that's just a general rundown of these sort of towing problems, right? A car connected to a trailer, something like that. That's the idea. So we have this sort of diagram. Hopefully you're comfortable with the forces I've added on. And the idea is to split up the car and the trailer separately to obtain what we want. Okay, so there we are. We'll be using this, what we've seen here now, with these questions now. Okay, so we're going to look at this exam question, which is going to involve towing. So we have a car of mass 1,000 kilograms in a straight line along a horizontal road, constant speed u. The resistance is 400 newtons. The engine is working at a rate of 16. That's by power, right? By power. That's 16 kilowatts. That's going to equal 1,600 watts. Okay. Now, again, if I draw the situation, I'll do it here. Again, I've got my car on a road. The mass is 1,000. Actually, draw. There we are. 1,000 kilograms. The speed is u. Okay, and it's a constant speed, which again means the acceleration. The acceleration is 0. Okay. And so then there'd be a driving force moving it forward, because again there's power, and a resistance force, which we told is 400, right? Now, we need to find the speed u. So again, we've got our power, okay? So power of 16,000 can equal the speed u times d, okay? Now, obviously, we need to find d before then we can find u here. Okay. How are we going to find D, my driving force? Well, let's just resolve forwards and backwards. Well, forwards is my driving force, take away the 400 backwards. And because there's no acceleration, it ultimately goes to zero. Mass times acceleration. No acceleration means it goes to zero. Okay. So D is 400. Cool. So there we are. So now we can sub D into here. So 400 times U. 400U is 1600. F for U is simply going to be 40. Okay, there we are. Cool. Now we're going to look at some towing. So now I'm told the car now pulls a trailer of mass 600 kilograms in a straight line along the road using the rope. Blah 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 blah. The resistance is still 400. Yeah, the resistance 400. And the resistance to the trailer is 300. And again, the power in the car is still 1600. Right, the tow rope is okay, blah blah blah. Okay, so we need to find tension in the rope. Okay, so quite a hefty paragraph there. Some of it's a bit waffle, but let's see let's sort of draw what's going on. So now we're on a road, but now there's a car towing the trailer. So I have my car, draw it quite big so we can add on our forces. So the mass of the car is 600. Oh no, sorry, the car's still 1,000 kilograms, sorry. The trailer has a mass of 600. Okay. Make sure you read your question. There we are. Again, if we then split halfway, there's tension either side. So towards the car, tension goes away, and then trailer, it goes that way. Okay. Right. Uh, okay. I'm also obviously the car will have a driving force, moving it forward. Am I told what it is? I don't think so. So I'll just call that D, the driving force D, right? Again, I know there's a driving force because there's power mentioned, okay? Anyway, I'm also told resistance. So the resistance force for the car is 400. So again, if the car moves forward, the resistance is 400 that way. And then the trailer has its own resistance, which is 300, okay? I think that's really it. Now, now it's going to be traveling at a speed. Has it? The speed, I assume, is still u. Okay, the speed is constant. Okay, so the speed is still going to be u, which is 40, right? And the acceleration, because oh no, sorry. No, the speed is different because they told us the speed is now 20 over 3. No, okay. My apologies. 20 over 3. Because it's a different situation now, right? It's pulling a trailer, so it wouldn't be the same speed now. My apologies. So they told us the speed is 20 over 3. Should have read the question there. Fully. There we are, though. That's the speed. The acceleration is going to be A. Okay, it's not a constant speed now, so the acceleration is not necessarily zero. But there we are. Right, I think that's everything to label. Okay, right, a lot of stuff going on here, but hopefully that made sense how I got to the diagram. Okay, again, once you get to the diagram, it mostly should fall into place. Really. So they want the tension, which again is this tension force T. So again, what I'm going to do is split up the car and the trailer separately. Firstly, let's have a look at the car. Okay. So again, just to make it easier, I'm going to draw it separately. Draw it out. Again, I'm driving force forwards. Again, then I've got my 400 Newton, my 400 and my T. Again, this acceleration is going to be A, and my speed is 20/3. Okay, so right, so again, I could resolve forwards if I want to. That's going to be D, my force forward, take away these two forces backwards, so take away 400, take away T equals MA. Now the mass is 1000, the acceleration is A. Now I can't do anything here. I don't know D, I don't know T, and I don't know A, so it's not really ideal. But what I also know is actually I know the power is still 16 kilowatts or 16,000 watts. I still know that, right? So I'm gonna I'll make a note that say also power is 16,000 watts. And I also know that power is speed. Now the speed I'm told is 20/3, right? Times my driving force. Therefore my driving force, if I do 16,000 divided by 20/3, put that in the calculator, I get 2,400 newtons, and there we are. I can add that on here. Okay, I'm going to box this equation here. I'll come back to that. Okay, that's everything to do with the car. Now I'm going to look at the trailer. Okay, now the trailer. Again, if I draw the trailer here, that's 600 kg. I have the tension acting forwards and the 300 resistance backwards. Okay, again the same acceleration there. Okay, and so then if I resolve forwards and backwards here, again use F equals ma. That's what I'm doing here. So again, my forward force is T. Take away the backwards force 300 equals ma. Mass is 600 times acceleration a. So we get this equation here. Okay. So ultimately, this is my equation from the trailer, and again, this boxed one is from the car. So if I combine this together, I get D. So if I copy the car one, I have D take away 400, take away T equals 1000 A. But actually, we do know what D is actually. Remember, we saw that D was 2400. So we can sub that in here. And so 2400 take away 400 is just 2000. So 2000 minus T is 1000 A. And then if we remember this equation we just got, we got T take away 300 is 600 A. And so these two equations now are simultaneous. So we can solve them. So firstly, well, if I rewrite this just a little bit, if I say minus T at 200, hopefully then you can spot we just need to add them to get rid of the T. So then I get 2000 take away 300 is 1700 equals 1600 A. Therefore, A is going to be 1.0625. And that's all the digits. Okay, there we are. Now I can sub that in to find T. So then if I substitute it down to this bottom one, T take away 300 is 600 lots of A, which is 1.0625. Therefore, T is going to be 300 at 600 lots of A. So I get T to be 937.5 Newton. And that, I believe, is the tension in the tow rope. There we are. Okay, so that's the whole idea, right? Again, we just consider the car and the trailer separately, and after that, it's basically the same sort of steps. Okay. So I've got this question here. There's no towing involved here, but it's a bit of algebra this time. Okay. So we're told a car is moving along a straight road, speed v. The resistance is this formula here. Okay. The power is 10 kilowatts. Again, I'm going to note that the power is 10 kilowatts, which is 10,000 watts. Okay, so if I draw the situation I have my car. They've not told me the mass of the car, weirdly. So I just have to leave it there for now. There's my car. The speed is v. I'll say v. The again, it's going to be a driving force d because there's power involved. But also there's a resistance force. Now the resistance force is actually this expression here, 150 add 3v. Okay, it's in terms of v. So there we are. But again, don't be thrown off by this. It's going to be the same steps, just with algebra with letters involved. They're asking me to work out the maximum value of v. Now, v is a speed, so the maximum value, it's just asking for the maximum speed essentially. But we know that max speed means the acceleration is 0. Okay, so I can add that on. 0 acceleration. Okay, right, so I need to find v then here. Okay, so firstly, again, I'm going to note my power. Again, so power is 10,000. That's going to equal my driving force d times speed v. Of course, to find v then, I'm going to need my driving force. If I resolve forwards and backwards, it's going to be d take away 100. D take away, now let's be careful here. I want to take away, obviously, this backward force. I'm going to do a bracket just to really signify I'm taking away the whole expression. Okay, that's going to equal 0 because the acceleration is 0. Okay, so F equals ma, that equals 0. Okay, if I now expand the bracket, do not mess up your algebra here. We're just doing some brackets here. D take away 150, take away 3v equals 0. Okay, and so what we have is that D is equal to 3v add 150. Okay, which is interesting. D is in terms of v as well. Okay, so I'm going to substitute it into here. So if I sub d into there, into my power, I get that v times d, which is 3v add 150, is equal to 10,000. Again, don't panic here. This is an equation, right? This is going to be a quadratic equation. If I expand, 3v squared add 150v equals 10,000, but then if I take that away to the other side, indeed I do get a quadratic, right? We know how to solve these, right? If I just stick this into the quadratic formula, so v is going to be minus 150 plus or minus root of 150 squared minus 4 of 3 of minus 10,000 all over 2 lots of 3. So if I put that in the calculator, but also I think the calculator should have a solve function where you could just instantly solve quadratics anyway. But there we are. I get v to be either 37.92 or v is going to be negative 81.92. Of course, we're going to then reject the negative answer as firstly maximum, right? So obviously the maximum out of these two is going to be the positive one. So there we are. And also, so there we are. So reject this solution. So V is 37.92 meters per. And there we are. That is my maximum speed. Cool. So again, this one looks quite unusual. There's a bit of algebra involved here, but you can hopefully see the steps are the same, so don't be put off by it, right? Okay. Now we're going to look at some more exam questions. Again, they love asking questions on this, so make sure you are comfortable with tackling these questions. So, okay. What we're told here is, and they're giving us a little diagram to visualize. We have a van, which we can see here, 600 kilograms, which is moving up the road. The angle is alpha, blah, blah, blah. The van's towing the trailer. And we're given some information about resistance forces. The power, the engine is working at 12 kilowatts. We should know that means it's power. So the power is 12 kilowatts, which again means in watts is 1200 watts. Okay? And it's asking for the tension, okay, given the speed of 9. That's actually quite similar to one of the earlier examples we just looked at, but it's quite meaty, 8 marks. Now, even though they're giving you a diagram, I do think it's helpful to draw it even bigger on your own, because there's going to be a lot of things we need to draw on. It's just not enough room, I don't think. Like, draw it really big like this, right? So again, we've got my car. Now, the car is 600 kg. That's towing a trailer like this. So this is my trailer. The trailer mass is 150. Okay. Now, right, we need to add on our forces. So, again, firstly, in the rope, there's tension either way. So this is the car, right? So the tension is going to go that way, and then tension that way for the trailer. And then there will be a driving force up the ramp at the car, because that's what pulls it forward. There's power. There we are. Then we got our resistance forces. We've got our resistance forces. So they told us the resistance of the van is 200. Okay, so at the van, which again is here, that's going to be 200 backwards. And then for the trailer, the resistance is 100. Okay. So hopefully with me here, right? How I got this diagram here. I think that's all the forces, I believe. Of course, there will be mass as well. There will be masses. So the trailer, if the mass is 150, the weight will then be 150 g. Okay. Likewise for the van, the weight is 600 g. Okay. Remember, weight is mass times g. And that's all the forces. Obviously, there'll be a reaction force, which will be different. Okay. R prime and but I'm not gonna overcomplicate it unnecessarily. So those are my main forces here. So hopefully you're happy with this. So then at that point, now we just start to form some equations, right? Let's do some resolving and use our power. So firstly, again, we're going to look at these things separately, as usual, as we just seen. So firstly, we're going to look at the car. So if I draw the car out, so again, I've got the angle alpha, got my van, not car, van. Van. My van, again, at 600 kg. It's going to have a weight of 600 g down here. The driving force is D, up the road. And then I've got my tension and the rope, and then the resistance presumably friction would be 200. Okay, so there we are. And also, there would be acceleration, okay, and a speed of 9, okay. So the speed is 9, and the acceleration is a. Okay, again, it's not 0 because it's not constant speed or max speed. Okay, we're just told the speed is 9. Okay, so that's everything, right? So I can add that on here. My speed is 9, and my acceleration is a. Okay, meters per second squared. Okay, cool. So okay, so hopefully you're happy with this. Hopefully happy how I just isolated the van forces here. Okay, I just separated to get the van only. Right. So again, if I now resolve up and down, I have, well, firstly the force up. The ramp is D. Take away the two forces acting back, which is 200. Take away the T as well. But also, in addition, again, the weight, which is why I included it, we need to include it. So that'd be 600G cos alpha and 600G sine alpha here. Again, this sine alpha part of the weight, that's going to also act down the road, down the ramp. Okay, so we've got this equation here. So my forward force up, take away these two forces down, and also the weight down in the same direction there. And that's going to equal ma, where the mass is 600 times a. Okay, right. So if I rewrite it here, I've got d minus 200 minus t, then minus 600g, that's going to be 600 times 9.8, so it's going to be minus 5880 sine alpha equals 600a. Okay, now this sine alpha, again, we're actually told what sine alpha is. We don't know what alpha is here, but we know sine alpha is 1 over 15. That's all we need to know, right? So actually, so this bit here, so minus 588, minus 5880 times sine alpha, which is 1 over 15, that goes to minus 392. Okay. So all I've done here, by the way, what I've done now is just simplified this. So what I did was 600 times g, which is 9.8, times sine alpha, which is 1 over 15. I got 392, just to clarify what I did there. Okay, right. So I got this. So I get this equation, and actually I can simplify it even more, just a little bit. If I do minus 200 minus 392, so d take away t take away 592 equals 600a. That's my final equation here. I can't do anything more. But what I also know with the van is the power of the van, which is 12,000 watts. So I also know that power is again, so my power of 12,000 is going to equal the driving force d times the speed. Now I'm told that the speed, as you can see here, is 9. Okay, so d times 9, therefore I get d to be 1333.33 newtons. So actually, then I can just actually simplify this equation even more, because now I know what d is. So therefore, 1333.33 take away t, take away 592 equals 600a. And that is the equation we get simplified. Okay. Right, that's the van. Now we're going to do the same for the trailer. Okay. So now if we look at only just the trailer, which is here, again, we're going to draw a ramp. We've got the trailer here. The mass of the trailer is 150. If you have, again, if you see here, got the tension force forwards, and then the resistance, which I think is 100. Yes. Okay. And then, of course, there will be weight that pulls it down, so that'd be 150G. Should probably split that up right in this way. So we've got alpha, so that'd be 150G cos and 150G sine. Okay, and then also I got my speed, which be 9. I won't need my speed here though, but I'll add it. And also the acceleration is A as well. Okay. Now, if I um okay, so if I use F equals ma, by the way, just to clarify, I'm not going to use power here. Power does not apply to the trailer because the trailer doesn't. The driving force is specifically tied to the car. It's talking the power comes from the engine of the van. So do not consider power from the trailer. Just to clarify. Okay. But anyway, the only thing we can do is F equals ma, like we are used to. So anyway, if I now look upwards, that's T, take away my downwards of 100, and then also the weight of 150G sine alpha. That's going to equal ma, where the mass is 150 times A. And actually, I can simplify this. T take away 100, take away 150G, so 9.8 times sine alpha, which is 1 over 15. That's in the question, is 150A. So if I simplify this, I get T. Take away 100, take away 150 of 9.8 of 1 over 15. I get minus 198 equals 150A. And that is my equation from the trailer. So again, if I then bring these two equations I've got together, so firstly I've got this equation here. So 133.33 take away T, take away 592. Oh, actually we can simplify this, sorry. So 1333.33 take away 592. It's going to be 741. 741.33 take away T is going to equal 600A. That's from the car, remember? That's, again, from this equation here that we've got. And then we use this equation too. So then we get T take away 198 equal to 150A. So we're going to got these two simultaneous equations here. Okay. And so at that point, we just solve them simultaneously. So first I could just add them together. So if I add them together, then the t's will cancel. So 741.33 take away 198, I get 543.33 equals, and then t minus t goes away, so then 600A and 158 is 750A. Therefore, I get the acceleration A to be 0.7244. Okay, I'll just leave it there, 7244. So therefore, T, if I sub A into, let's say, the second equation down here, so T take away 198 is 150 lots of A. Okay, so therefore T, if I solve this, the 198 add 150 lots of 0.7244. I get 306.7 newtons to 2 decimal places. And that's by tension, which I believe is what they wanted. Yes, the tension in the tyre bar. There we are. 8 marks there. Okay, so hopefully, again, make sure you look through it step by step. Hopefully, even though there's a lot of stuff going on, the steps make sense, and you'll start to see it's the same sort of stuff every time, really. But there we are. Okay, I'm going to finish off with this one. And it's very hefty, very quite a hard question, and kind of brings everything together because you can see there's work energy principle involved as well at the end. So here we are. Okay, so firstly on this block of text, we're told a car pulls a trailer of mass 150 on the straight road. The trailer is connected by a light and extensible tow bar. Resistance of the trailer. Okay, blah blah blah. Right. So if I draw the situation again, so what's happening is I've got a car towing a trailer on a straight road, like this. I've got my car. The mass is 600 from the car. Again, then that's towing a trailer. The trailer is 550 kg. And again, then if I split it in the middle, tension acts away from the car and pulls the trailer forward. So those are my two tensions, either side. There are resistance forces. So the resistance of the trailer is 200 newtons. So from the trailer, 200 to here. And then the car, the resistance of the car is in terms of V. It's this 200 add lambda V. So this lambda is just, again, it's like a number, right? Okay. So then we're told when the engine of the car is working at a constant rate of 15, so that's my power, right? So I'm told the speed is 25. Okay. So I'll make a note of that. So the speed is 25. And I'll also make a note that the power, which it is, what's the power? 15 kilowatts. So again, we need to convert that to watts, for 15,000 watts. Okay. Now the acceleration, the speed, we're told is constant. So that means the acceleration has to be 0. Okay. So it makes it a little bit nicer to deal with here. Okay. So there we are. Of course, there will also be a driving force D. There will be a driving force D because there's power. So there we are. Driving force on the car that moves it forward. Right. I think that's everything. Well, actually, we know that the speed is 25. So V. So the V involved in the resistance V is 25. So actually, we can just say lambda V is 25 lambda straight away. Okay, so there we are. So we'll just need to show that this lambda here is equal to 8. So let's see what we can do. So again, what do we know? Well, firstly, again, the usual strategy is we're going to split things up. So firstly, let's just consider the car. Again, the car, 600 kg, driving force D, 200 plus 25 lambda. Then T, and then there's a speed of 25 and acceleration of 0, right? Okay, so if I do F equals ma, actually tell you what, first we'll deal with power, actually, because we know that the power also is 15,000. Okay, so that's going to equal speed times driving force. We know the speed is 25 times the driving force D. So actually then we can quickly get driving force to be 600. So there we are. We can add that on. Okay. Right. So hopefully with me here then. So then we can start resolve. Look forwards and backwards. So firstly 600 forwards. Take away t. Take away also this whole force here. So 225 of lambda in bracket. I'm going to take it all away. That's going to equal a 0 because the acceleration is 0. Okay, so if I just expand this, I get 600, take away t, take away 200, take away 25 lambda equals 0. So actually then it simplifies to 400, take away t, take away 25 lambda equals 0. That's my equation here. Then I'm going to do the trailer, right? So now I'm going to consider the trailer on its own. So again, the trailer is here. 150 kg. Again, there's going to be the T force, tension forward, and then this 200 resistance backwards. Again, the acceleration is 0. There we are. So if I now again resolve forwards backwards, that's going to be T take away 200. It's going to equal 0 because again, no acceleration. Therefore, T is simply 200. There we are. So actually then I can substitute T into this equation we found from the car, right? So 400 take away T, take away 25 lambda equals 0. If I sub T in, 400 take away 200 equals 25 lambda, right? Therefore lambda. Actually, I'm going to break it down. So then 25 lambda is going to be 200. So therefore lambda, if I divide by 25, I get 8. Well, that's great news because that's what we needed to show. There we go. So now part B. So now let's have a look at the rest of the question. This is where it gets spicier. Okay. Now we're told later on the car is pulling the trailer up a straight road, inclined at an angle theta. So it's inclined. So again, it's up an angle now, right? It's going to look like this, right? Anyway, so the car is pulling the trailer up a ramp. The resistance, we're told about the resistance forces, blah blah blah. We're told the engine of the car, again the power is 15 kilowatts. Okay, that's the situation. So a car is pulling the trailer now up a ramp. But what we're told here is when the speed goes to 10, the tow bar brakes. So now, what that means is they become disconnected. So you can imagine the second speed hits 10. Again, if I draw the situation, the speed reaches 10. The We have our car, we have our trailer. Now the tow rope that connects them when the speed goes to 10, it breaks, it snaps. Okay, so they're no longer connected. Okay, they're separate. They're completely separate now. So that's when the speed reaches 10. So then the tow bar brakes, they are decoupled from each other, so they move separately. The trailer comes to rest after moving d meters after the tow bar brakes. And then in part B, it says find the acceleration of the car immediately after the tow bar brakes. So if I draw that situation of the car immediately after it brakes, okay? So after the tow bar brakes, this is the situation with the car, okay? So the car is no longer connected to the trailer as we just discussed because it snaps when the speed is 10. So we just have the car to consider on its own. So the car again has mass 600 kilograms. It's still going to have a driving force because the power, remember the power of the car is still 15 kilowatts or 15,000 watts. So I'll make a note of that. The power 15,000 watts. There's still going to be a driving force. It might be different now to the one in part A, right? Because the speed is changed. Okay, so a new driving force D dash. And then we got our there won't be a tension force anymore, because remember the T force, the tension here in the rope is gone because the rope has broke. So there's no tension forces acting on either vehicle. The only the only force backwards with the car is the resistance, right? Now the resistance of the car, we're told, is this 208 V. I'll add that on. Okay, so it's in terms of V, the speed, right? So we have this situation here, 208 V. Okay, of course there would still be mass, weight, sorry, of 600 G, so mass times G. Again, then if I split this up as like this, I have 600 G cos theta. Again, if we use SOHCAHTOA, this is my right angle, 600 G is my hypotenuse here. Then a 600 G sine theta there. Okay, those are all my forces now. Okay, so you can see the car is completely separate. There's no rope anymore, no tension, anything like that. So that's my full diagram, okay, that I need. Of course, there would be speeds. So the speed, so when the trailer brake, when the tow bar brakes, the speed is 10, V is 10, okay? So I'll make a note of that. So 10 speed. The acceleration is A. Now that's what he wants me to work out for part B. He wants me to work out the acceleration of the car. Okay. So that's everything. But actually, I think we can actually simplify this resistance force, right? Because it's 208 V. But we know that V is 10. So actually, if I just do it roughly here, I'm going to say the resistance is 208 V, but we know that V is 10. So actually, 200 at 8 lots of 10 goes to 280. So actually, I can just simplify this to 280. And there we are. Okay. Right, and that's everything. So I need to find the acceleration. So what can I do? Well, firstly, again, I know I have power. So power is 15,000. That's going to equal my driving force D prime times the speed, which is 10. Therefore, my driving force in this situation is going to be 1500. Okay, so I can add that onto my diagram then, right? 1500. And there we are. Okay, now I'm going to resolve to get my acceleration. So if I now resolve up and down the road, well, firstly upwards is 1500. Take away the this force down, but also the other force acting down in that way is the 600 G sine theta. And that's going to equal MA. Well, the mass is 600 from the car. Lots of A, the acceleration. Okay, well, actually, we can simplify this. So, 1500 take away 280 is 1220. And then minus 600 G sine theta. Well, 600 G is 9.8 times by sine theta. Well, actually, in the question, they told us sine theta is 1 over 15. So we can just plug that in. So that would be 600A. So if I simplify this even more, I get 600A is 828. Therefore, my acceleration divided by 600 I get 1.38. And there we are. That's my acceleration, meters per second squared. Cool. Then part C. Part C. So part C is then asking, use the work energy principle to find the value of D. So now, so remember what's going on is after the tow bar breaks, we're told the trailer comes to rest after moving D meters up. So the situation there is obviously once the tow bar breaks, the trailer is on its own, right? The trailer is on its own. It's gonna move. It's gonna have some speed, right? It's gonna have some speed. Um, it's gonna have some speed. Well, 10. It's gonna have speed of 10, right? Because they share the same speed. So it's gonna have speed 10 initially. So it's still gonna move up some more, but eventually, because the trailer is unsupported, it's gonna come to rest with 0 speed. That's the idea. Okay, so if I draw that situation on here, if I draw this here now with the trailer, so now I'm drawing the trailer's perspective after the tow bar breaks. So again, my ramp, theta, my trailer, the mass is 150 kg. Now, as I discussed, the trailer, obviously the trailer was connected to the rope with a tension force, but that's gone away because there's no rope. So there actually is no force forwards. So the only force backwards, obviously we've got a weight, which is 150 G, but resistance wise, that's going to be the resistance force we're told is uh, 200 newtons. That's the resistance of the trailer. So 200 newtons backwards. Okay, so hopefully with me here then, that's pretty much the setup. Again, it will have speed. What happened is it has initial speed 10. That's the moment the tow bar breaks and they're disconnected, and then eventually it will have speed 0. Okay. So there we are. Okay. So that's pretty much the setup. Those are the forces really. So they want so the idea is the trailer has moved a distance d meters up the ramp after it breaks until then it goes and stops. Okay, if they want me to find the distance d, it moves up the ramp between these two speeds using the work energy principle. So remember then, cast your minds back to the last part. We said the work energy principle from last time, that the change in kinetic energy, add the change in GPE, is equal to the overall work. Okay, and so the overall work, again, remember, if I just draw a little rough diagram, if I have a driving force forwards and a friction or a resistance force backwards, the overall work, I'll make a note of it here, is work forward. So the work of the forward force, which is D, to work forwards, take away the work backwards. We could squeeze it in here. Okay, work backwards, so the work of friction force. Okay, so there we are. Okay, so that's the work energy principle. Hopefully you're familiar with this. So firstly, we're going to need to work out a change in our energies. Firstly, the change in kinetic energy. Well, as we have here, we have the initial speed is 10 and then it goes to 0. So the change in kinetic energy, or the final is 0. So it's going to be 0 take away half mv square, half m of 10 squared. So half of 150 for the mass times the initial speed, which is 10 squared. If I work that out, I get 7,000 minus 7,500. Again, it's negative because it's a loss, okay? But let's keep it, let's leave it as a negative. Then the change in GPE. So now we're looking at the change in the gravitational energy, so the height change. Now the height change is the vertical height. So if we're going up the ramp by d meters, what's the vertical height? This height here. To work out that height, we're going to need to do a triangle to help us see. Okay, so our theta here, this is my height h I want to work out. If I'm going up the ramp by d, I can say that the height h is going to be, if we use a bit of SOHCAHTOA, it's going to be d lots of sine theta. Okay? So remember, sine is opposite over the hypotenuse. H is the opposite. D is the hypotenuse. So therefore, what is it? Sine theta is h over d. For times by d, d sine theta is h. That's where that comes from. Okay. Right. But we also know sine theta is 1 over 15. So actually h is 1 over 15d. So that is the height change. Okay, so the change in GPE is mgh, if you recall. But the mass is again 150 times 9.8 g. And the height is 1 over 15 lots of this d. It's going to be positive because it's going up. It's going up the ramp. We can simplify this to 98 lots of d. Okay, therefore I can now use this work energy formula up here. So if I use it here, the change in kinetic energy is minus 750, and the change in GPE is add 98d is going to equal the overall work. But as I discussed, the overall work, again, if an object is moving forwards by a force and backwards by a force, it's going to be the forward force take away the backwards force. The work done forwards take away the work backwards. Well, of course, with the trailer here, there is no forward force. So actually, the work, if there's no forward force moving it forward, there's no work done forwards. Quite simply, okay, there's no forward force and no work done forwards. So this goes to 0. So therefore, if we that means minus work backwards is going to equal 98d minus 7500. Okay, so hopefully with me here. That's the simplified equation. So then we can just simply divide or multiply, whatever you want to do. I want to flip the negatives, essentially, is what I'm doing. So therefore, simply work backwards. So the work done backwards is going to equal, if we're going to flip the negatives, it's going to be 7500 minus 98d. Okay, hopefully you're comfortable there. Just flipping the negatives to make the work backwards positive, because there's a negative here, and that is because we're taking away work backwards here. Okay, and there we are. So that's work backwards. This is the work done by the backwards force. Now the backwards force is the 200 Newton resistance. So that we can actually work that out then using the work formula, which is work is force times distance. Okay. So that means work done backwards. Well, the backwards force is the 200 newtons, and the distance travelled is d. So there we are. So that means if we substitute that in to here, the work done backwards is 200 lots of d. It's going to be 7,500, take away 98D. And so at that point, it becomes quite simple to solve for D. So 298D is 7,500, therefore D is going to be 25.17 meters, 2 decimal places. That is the value of D there. And there we are. That's that question done. Very, very meaty, potentially horrible question there. But a somewhat interesting question. It combines everything we've done together in one question. So if you really want to test to make sure you know everything in this chapter, this is a really good question to go over to make sure you understand. Okay, it brings everything together in one. So there we are. So hopefully, if you go step by step, that makes sense there. But that's it for now. It's the end of this chapter. But that's it for now. I'll see you next time.